Okay. So we know dg is equal to vdp minus sdt. This was true for constant composition system where we were not worrying about composition. And then we added that if the system is made up of different species, then we can account for it basically by adding mu I dni, where mu I is partial g by partial ni at constant temperature, pressure, and nj not equal to I, right? This was the most important equation we studied last time. And due to this, directly it follows that du is equal to TdS minus PdV plus summation I mu I dni. Now this mu I is the same as here. Even though you are talking about du, you can show that it is the same as calculating partial g by partial ni at constant temperature, pressure. However, if you look at this equation, you can see that mu I is also the same as partial u by partial ni, but this time keeping s and v constant, right? S, v, and j not equal to I. So it so happens that these two are equivalent. And similarly, we can have definitions for chemical potential for other things. So this is one thing we did. Then we showed that we went over to partial molars. Partial molar quantities can be, so this is all recap. Partial molar quantities, which are denoted by a bar on their head, so G bar, V bar, A bar, H bar, U bar, any of these, they can be defined by thinking about how the G depends on number of moles of particular species. So in this case, for GI bar, for Gibbs free energy, GI bar is equal to mu I, right? Because GI bar, but for other things, if you have volume or if you have internal energy, then you can again write U is equal to I ui bar ni, but ui bar is defined as partial u by partial ni, keeping constant temperature, pressure, nj not equal to I. So you can see this is not the same as this one, right? Because when we are differentiating internal energy with respect to ni to get chemical potential, we keep S and V constant. Those are the fundamental variables for U. And this is why this fundamental variable concept, one of the many reasons why it's so important. But here you have temperature and pressure. It's only Gibbs free energy for which partial molar happens to be the same as the chemical potential. Okay, it's got a special relation given the fundamental variable for G. So let's call this as equation number 1. And equation number 1 can now be written as G is equal to mu I ni, right? It is a sum of mu I multiplied by ni. So if you differentiate this, what will you get? You will get dg is equal to summation I mu I dni plus summation I ni d mu I. Everyone happy with this? Right? It's just a function. I have differentiated it. I have applied the sum rule. What else do I know about dg? Let's call this equation 0 because I forgot to number it. And let's call this equation 2. Equation 0 says dg is equal to v is equal to summation I mu I dni plus vdp minus sdt. So if we compare 0 with 2, we get something interesting, right? If you compare, this is dg, this is the same. So it means these two things must be the same. Therefore, summation ni d mu I is equal to vdp minus sdt. This equation has a name. We wrote down the equation last time. We did not derive it. It's called Gibbs-Duhem equation. Do you want a Snickers bar? No? Okay. Maybe later. So this is Gibbs-Duhem equation. It is talking about the number of moles you have of a certain species multiplied by the change in chemical potential of that species. It's not obvious at this point why it is useful, this is a good spot to derive it. We will be using it later. Basically, if you can imagine a scenario when the chemical potential is changing, it's a constraint or the system. Most importantly, more specifically, the Gibbs-Duhem equation, you will see in the following form. So equation 3, which we wrote down as Ni d mu I is equal to VdP minus SdT. This is Gibbs-Duhem. Often you will just see it written as in this form. Ni d mu I is equal to 0 for constant temperature, pressure, process. So both of these, some books call the first one as Gibbs-Duhem, some books call the second one as Gibbs-Duhem, but this is our Gibbs-Duhem equation. At some point we will use it. For now, if you want to forget about it, that's okay. What you should not forget about is the definition of chemical potential. Okay, we are going to be spending a lot of time talking about it. Any questions? Okay, so now that we have talked about chemical potential, we are ready to move on to talking about how to represent, how to talk about really systems with variable composition. So this was all recap. Let's talk about what's going to happen in this week's class. So we are going to talk about the concept of a phase. Then we will talk about the concept of a phase diagram. We will briefly talk about the concept of a phase transition. These are all complicated topics. When I was an undergrad, my undergrad degree was in material science before I moved on to chemistry. I had full semester, 4 months of one class on phase diagram, then full 4 semesters on phase transition. And you can keep spending a lot of time on these. We will be quickly surveying this and basically equipping you. My point here is to equip you, make you capable of understanding what is a phase diagram, looking at the phase diagram and making sense of it. And more importantly, telling you how to find more information if you need it. So then we will do phase transition. And after that, we will be talking about something called Gibbs phase rule, which is a very interesting rule that applies to phase diagrams. And so this is this week's plan. And we will then talk about phase boundaries, equations for phase boundaries. And it will all make sense once we basically talk about what is a phase. And this will lead us to 2 equations called Clausius-Clapeyron and Clapeyron. So this is what we are going to do next. And finally, this will allow us to explain as to why all you knew about ice skating was wrong. I mean, you don't need to know how ice skating works in order to skate, right? I think I kind of know how it works, but I'm a terrible skater, right? So understanding how something works is not important to being good at it often. It happens in life. So let's start with what is a phase. So the point of doing all of this is to think about, and even though I said phases and phase diagrams apply to variable composition system, yes, they do, but you can think of a phase diagram even for a single component system. The simplest phase diagram is, well, actually it's anything but simple, but the most popular phase diagram is, there are 2 phase diagrams which are very important for life or society. Does anyone know which are those 2? The Snickers bar is up to step. Water. You don't have peanut allergy, right? He's eager. And where are the material scientists? Biology. Oh, in biology, there are also lots of phase diagrams, but there is one which has affected us in every possible way for the last 1,000 years or more. Even it's so important that ages are named after it. You know, parts of humanity are. Go ahead. Iron carbon phase diagram. No peanut, right? Okay, sorry, you can find it. So the iron carbon phase diagram and the water phase diagram are possibly the 2 most important phase diagrams. The iron carbon diagram is quite complicated. The water also gets complicated, but the simplest. So for example, we can think about the water phase diagram, or we can think about the iron carbon phase diagram. Why carbon? You said iron, so I should take half the Snickers bar back. It's not just iron which matters, it's mixing carbon matters, because when you mix carbon and iron, you get steel, right? And that's we can come up with lots of fancy materials or chemicals, but iron and steel are always going to be very, very important. So these are two very important phase diagrams, and there are many, many more. In biology, you will look at phase diagrams of proteins. For example, when is a protein folded? When is a protein unfolded? What happens when we add some contaminants to it, and all those type of things. But the basic idea behind a phase diagram is it's a map with two coordinates. This coordinate could be pressure, and this coordinate could be temperature, okay? So it's a map. Let me write it down. So these are just examples. So a phase diagram is a map with any two intensive variables. Any more than equal to one intensive variables. You can also make a phase diagram in just one variable. Typically, we will talk about binary phase diagrams where we have two variables. You can have ternary, you can have quaternary phase diagrams. It keeps getting more and more complicated. So it's a map with more than equal to one intensive variables and areas drawn in this map. So what do I mean by this? So let's think about the water phase diagram. The water phase diagram looks something like this. You have one line which goes like this. You have another line which goes like this. And you have a third line which goes like this. In this pressure and temperature, when your temperature is low enough and your pressure is high enough, so when your temperature is low enough, when you cool water more and more and more, what do you expect water to be? Solid, liquid, or gas? Solid, right? So most of the time at very low temperature, water will be solid. But if you decrease the pressure too much, it will start to become a gas, right? It does not become a liquid. It straight away goes into a gas, which is kind of interesting. So this phase over here is a gas. And this third phase on top is liquid. The boundaries correspond to when liquid plus gas can coexist, and our superior knowledge of free energies will allow us to calculate what ratio they can coexist in. Over here, we will have solid plus gas coexisting. Over here, we will have solid plus liquid coexisting. What will we have over here at this point? Go ahead. Yeah, but that's very easy. I'm not giving you a candy for it. That's all three coexist. This over here is a very interesting point. So this point that all three exist is called a triple point. And this is not a point where I just drew lazy and stopped drawing my line. It is an actual point where the line stops. This one is called a critical point, and we will study a little bit in what happens at critical points. It's a very funky space. It's a very funky point in phase diagram where all sorts of bizarre things happen. We'll study a little bit about that. So this is your first introduction to a phase diagram. You could have a phase diagram in some other space. You could have a phase diagram where instead of pressure and temperature, you could have some other intensive quantity. So what other intensive quantity can you think of for phase diagrams? So phase diagram axes could be from, we just saw pressure and temperature for water, but what else could it be? Go ahead. Just keep naming intensive variables and then we can pick. Huh? Mole fraction, what else? Is that intensive? No. Density is, right? Okay, I'll give you a kind of. Don't get smacked. So what else can you think of? No ideas? Anything else? Be creative. For a magnet, it could be magnetization. We mentioned iron, right? For iron, we could think about whether it has a net magnetic moment or not. Using the average magnetization, you could distinguish whether iron is antiferromagnetic or ferromagnetic, right? And you could have a phase diagram in that space. So you can do lots and lots of things. These phase diagrams could be from all all of these, any two variables. Typically, most phase diagrams focus on pressure, temperature, and mole fractions. Although this phase diagram for water, if you try to plot it in pressure density space, it becomes very non-trivial, this diagram over here. So water is the simplest phase diagram drawn in pressure temperature space. When we talk about the iron carbon phase diagram, it is in temperature composition space. So but the idea is your axes are always two intensive, one or more intensive variables. So when you have two variables, a phase diagram looks like a graph like this. When you have three variables, a phase diagram tends to look like a triangle. And we will not be talking about it. This one is called a Gibbs triangle. The material science students will be talking a lot about it in their core classes, but here you correspond to composition. And basically, if you have, for example, if you have three chemicals existing together, this will be pure A, this will be pure B, and this will be pure C. And then lines that go like this will correspond to decreasing amount of A. So in this class, we will not be talking about ternary phase diagrams. We will restrict ourselves to binary phase diagrams. So this is a ternary phase diagram, while what we did on the last page is a binary phase diagram. And we will restrict ourselves to talking about binary phase diagrams. So the water pressure temperature phase diagram, even though it's so important, it's still a work in progress, because what happens is that in this solid over here, I just called it solid, which is ice is always one form. Turns out ice has different crystal structures. And as you keep increasing the pressure, the crystal structures of ice become more and more and more complicated, and people are still discovering. So at very high pressures, these crystal structures of ice matter a lot. Can anyone imagine why they matter? Why should anyone care about the crystal structures of ice that, so it could be something like this. This is one phase, this is another phase, this is a third phase. It could be whole patchwork inside this. Why should we care about that? Any ideas? It's again very important to life. More importantly, our search for life. Go ahead. So when people go around looking for water in,
You're going to get different spectra from the ice.
That's true. But why would you say it's important to, I don't know, your grandma? Would your grandma, unless she's a scientist, think that's important?
Well, when you shine your telescope at a planet, you're expecting to get different spectra of action.
That's still assuming your grandma is very important. It's very technologically good. She might be. I'm looking something basic. Someone else raised a hand? It's related to what you're saying, but think big picture. How would you communicate to someone on the road? Why should they care about ice at high pressure? When people go around looking for water in the cores of stars or things like that, or on extra planets out there, the search for water in the outer galaxy is not in water in the liquid form. It's search for water in some complicated solid form. It's ice in some strange, like Saturn actually has ice in some complicated solid phases, So, and the temperature is very low, right? So you are in this part of the axis, and the pressure can be anything. Who knows what's the pressure at the core of a star or in the atmosphere? So people are very interested in figuring out the phase diagram of water. And currently ice has at least 15 different forms in the solid phase. And it's still, people are still continuing to find more and more different forms of ice. Does anyone know what's special about ice 9? And this has nothing to do with chemistry. No one knows ice 9? It's the name of a novel by an author called Kurt Vonnegut. You should read it. It's very good. His other book is called Slaughterhouse-Five. So that's ice. The phase diagrams get very complicated. We will not be getting into very complicated phase diagrams, but we will learn the basic concepts of what goes into a phase diagram. And so I just introduced to you what is a phase diagram, but now we need to get a bit more clear about what is a phase, right? Before we start talking about phase diagrams, we need to define the concept of a phase. So what I'm going to do now is to define 3 different concepts. Do I need to do all 3? No, let's just start with a phase. So in order to define phase, I will define it in the following way. A phase is a region of space, space as in here, not just outer space, just anywhere, region of space throughout, someone is very bored, throughout which all properties of a material, it could be a chemical, it could be a polymer, it could be anything, are uniform. But what do I mean by property? By properties, I mean density, refraction index, magnetic moment. So you cannot distinguish part of this from another part of this. This is all in the same phase by doing some experiment. On an average, it will have the same refractive index. On an average, it has the same density. Yes, there will be fluctuations locally, but on an average, it is the same. So this is our definition of a phase. Now, it's important to note, just like I pointed for ice, that same solid can exist in different phases, right? So just because something is solid does not mean it's all the same phase. You could have a solid material existing in 2 different phases. For example, in this homework, in the first problem, when you have 2 polymorphs and maybe both of them coexist, you have 2 different phases. They will have their own different properties. And if they are coexisting at the same time, you have 2 different phases. So when a solid exists in different phase, how do you distinguish, what do you expect to be different between a solid that exists in 2 different phases? What are the type of things that can be different? Like in ice, I said ice can exist in different phases. Go ahead. Melting point will of course be different because melting point is dictated by when you cross this line in the phase boundary, right? So of course it will be different, but even simpler, crystal structure will be different, right? One could be FCC, one could be BCC. So of course they will have different melting points, different crystal structures, ... So it will have different properties. So same solid can exist in different phases. Just because something is solid or just because something is liquid, it does not mean it's all the same phase. At the same time, you can have more than one element mixed and still have only one phase. What examples can we think of this? Go ahead. Alloys. Can you name an alloy?
Steel.
Okay, steel, iron plus carbon, right? You mix them, you could have one phase. You could have more phases also, but just because iron and carbon is mixed, you want a candy? You can. You are ready to go. I have. So, and water, right? Just because you have H and O does not mean it's all same phase, right? Water is another example. You have hydrogen and oxygen mixed, and it's all. Go ahead. Yeah, sure. But I'm saying just because you have 2 elements, even in water, water could decompose into H2O, H3O plus and OH minus, and then things could get complicated. And I just said for water that water, if in solid form, could have different phases. But just because you have 2 elements does not mean you have different phases. You might not. And alloys actually get even more complicated. There is something called high entropy alloys, where you have 5 different elements mixed together. You will have things like cobalt, chromium, iron, manganese, nickel, and yet it will form one phase, which is very peculiar, and not many people understand as to how this happens. They are entropically stabilized. So phases, so the recap of this part is that A phase is a region of space in which a material has uniform properties. This could happen even if the material has 5 different elements mixed in it, 10 different elements mixed in this, or even if there is only one element, even if you have hydrogen and you could have liquid, solid, and gas existing together and you have 3 different phases, right? So you have to check for, are the properties differing or not in your sample? So that's our phase. We already looked at phase diagrams. A phase diagram is a map of how these phases exist. So for example, in water, do we have only one phase or not? In order to answer this question, we have to go and look at the phase diagram. And the third concept that I want to talk about after phase diagram is that of phase transition. Phase transition is the change from one phase to another. And generally, but though not always, generally, phase transitions are studied at certain pressure and temperature. This doesn't always have to be true, but this is typically what is done. You talk about the change in phase at a particular value of the pressure and at a particular value of the temperature. So let's say we have 2 possible phases. Let's say we have phases alpha and beta at some temperature T and some pressure P. And I know, so how should I tell which phase will be more stable? Someone who has not answered. Hannah, you're very quiet today. You don't want a Snickers bar? You know this. Gibbs free energy, right? So what should I say about G alpha and G beta? Which one should be smaller for alpha to be stable? G alpha should be smaller than you want. I have a lot of candy left, so there'll be a lot of Snickers next few classes. So if G alpha is less than G beta, alpha is stable phase, and vice versa, right? So it's the Gibbs free energy that allows us to calculate which phase is the dominant phase. It allows us, and we will see soon this week that it not just that, it also allows us to calculate the temperature and the pressure at which a phase transition will happen. As you saw in the polymorph problem, you kind of got a flavor of that in this homework, that you can go and calculate the pressure at which another polymorph becomes stable. And we will be doing all that in a systematic way over here. So dG at constant temperature pressure less than 0 is the criterion for spontaneous phase transition. And I want to emphasize here that spontaneous is not the same as instantaneous. Let's take water, for example, right? Let's say this is pure water and I start adding sugar to it, right? I start mixing in some sugar. So I mix a very small amount of sugar. What's going to happen? It will dissolve, right? As I add more and more sugar, what do you expect to happen? Huh? Go ahead. But I added even more. Will it still keep dissolving? Then what will happen? It will crystallize, right? You will start precipitating small crystals of water, of sugar. So it does not mean it will crystallize instantaneously. It still might take time. So when we get to the kinetics part of this class, we will see that phase transitions, just because they are thermodynamically going to happen, does not mean they will happen right away. Any questions about this? Phase and phase diagram and phase transitions. This was quite easy. We have just set up our groundwork of how to study all this. Go ahead.
So then according to our definition, for ice, for example, it has the same property you had like 0 degrees Celsius and like -100 degrees Celsius. That applies.
If it is in the same, So a phase is defined at a particular temperature and pressure. If you start changing the temperature and pressure, then it could form a different phase.
Okay.
Yeah, so we are talking about a particular point at a certain temperature and pressure in this case.
So phase refers to a particular point on the phase diagram.
Yeah. If you have other intensive quantities, you have to think about those intensive quantities. Yeah, but good question. So we did phase diagram, we did phase transition. The fourth thing that I need to introduce to you is where it starts to get a bit confusing. It's called component. Thankfully, we are not going to worry about multi-component systems. Well, we will worry about multi-component systems, but I will tell you how many components are there. The hard part about components is calculating how many components are there, and I will show you why. So a component C is a chemically, so in phase, we talk about physical properties, right? That you can measure. Now I'm talking about chemical property. So this is a chemically independent constituent of a system in other words, it is the minimum number, let me write it down, then we'll go through it, of independent species required to define the composition of a system. So if you have just water, and this could be solid water, liquid water, gas water, we don't care. We are not talking about the phases here. You have just water and you know it's not changing into hydronium, it's not changing into hydroxyl, no hydrogen peroxide, nothing. Then the number of components is equal to 1. Okay. At the same time, now if you know that water is actually undergoing autoionization and you're forming H3O plus OH minus, then how many components do you have? And let's say this is existing at equilibrium. Any ideas? Go ahead. 4? 3? You will get it at some point. Both are wrong. Huh? Even 2 is wrong. Go ahead. Yeah, it's the dependencies that makes things complicated. So I have 2 last pieces of time. You can take them. So in this case, the number of components is 1, and that's really confusing. Why is it confusing? Because we have 3 species. We have water and hydronium and hydroxyl, right? So it should be 3. But on top of that, we have 2 constraints on the system. The first constraint is chemical equilibrium, and the second constraint is charge balance. So this is confusing. So let me write down what happens in presence of constraints. And like I said, thankfully, I will not have you calculate the number of components. I will tell you what are the number of components, but I want you to be aware of the formula for your practical life if you need it. So this is the best formula to calculate is the number of distinct chemical species. So if you had nothing happening, if you just knew that you had water, liquid water, H2O, hydronium, and hydroxyl sitting, and the whole thing could be fully charged, it doesn't have to be charge neutral, and if there is no chemical equilibrium forcing them to stay in equilibrium, then C would be equal to 3 in this case. It won't be 4, like you said, Stella, because that is just balance. You know, we are not, no, it's okay. I would have also said 4 because you see that 2, and I think it's 4. So first thing you have to do is to look at number of distinct chemical species. So in this case, there are 3, right? Liquid water, H2O, H3O plus, and OH minus. But then you have to subtract out the number of chemical reactions because each reaction is an equilibrium condition, which is a constraint. And then you have, which is one type of a constraint. And I'm here following Atkins convention, which is also making it a bit confusing. Atkins doesn't do a very good job here. I would have just called a reaction as a constraint. But then they distinguish between reactions and other constraints, and then number of other constraints. In this case, one of them is charge balance. So this gets confusing. And every year, just like, remember in the beginning of the semester, you were all so wound up over degrees of freedom, right? Everyone was like, oh, how do I calculate degree of freedom? I was like, let's not worry about too much. What you need to remember is that internal energy is proportional to degrees of freedom. And you will study it in 482. You will need to go and calculate how the energy levels are separated and things like that, but it's messy. This is one of those things which also gets confusing. So one thing you can always keep in mind here is that C, the number of components, if you calculated the total number of species in a system, can C ever be more than the number of species? No, right? Why, Corina? We have subtracted two things from it, right? So if there was no chemical reaction, no constraint, C would be equal to number of species. So in general, C is going to be less than equal to the number of species. This is one thing to keep in mind, okay? How much less? You have to go and calculate the constraints. It's not that bad, but I don't want to get into it too much because it does get confusing sometimes. I want to do one more example of this. Let's think about calcium carbonate changing to calcium oxide plus carbon dioxide. What is the number of components here? What's the number of species? 3. What's the number of chemical reactions? Do we have any other constraint? Charge is not involved here, right? So in this case, this is going to be 3 minus 1 minus 0 equal to 2. Okay, so this is the number of component. So we learned a few new concepts so far. We learned the concept of a phase, which is physically looking same at those values of the intensive quantities like you pointed out. If you're going to change pressure and temperature, then it becomes different. Then we talked about component. And we also, of course, talked about phase diagram and phase transition. We talked about component. Now I'm ready to introduce to you the Gibbs phase rule. Now that we have done both of these, Gibbs phase rule says, and this rule is really, I like it a lot. It's actually a bit of fun, that the number of degrees of freedom of a system is given by C minus P plus 2. And we will just see in a moment what is number of degrees of freedom. Sorry about this. Okay. So Gibbs phase rule says that, so this is the third quantity. This is number, or no, we don't need to write number. We can just call it degrees of freedom is equal to FC minus P plus 2. So you might think, why this is so abstract? Why do we have to do all this? Well, you all nodded your heads when I drew the water, especially Daniel, he really nodded his head. When I drew the water pressure temperature phase diagram, right? Let me ask you a question. Why is it that solid and liquid have to exist along a line? Why could we not have a whole area of solid and liquid existing? So let me rephrase this. So in this water pressure phase diagram, I said that maybe it's water, maybe it's something else, some phase diagram. Don't obsess over this line. How was it in water pressure? Yeah, let's try it this way. Some line which exists like this. So notice I said, this is all solid, this is all gas, this is all liquid. And I said the line is when solid and liquid coexist. And this line is when liquid plus gas coexist. And this point is when solid plus liquid plus gas coexist. So see, I've been making an assumption over here that in pressure, temperature, one component phase diagram, this is only water, okay? There is no autoionization going on, it's just water. So I've just assumed here that in pressure, temperature phase diagram, for one component, two phases exist along a line one phase exists along an area, right? A single phase can exist in a whole area. Two phases can exist only along a line, and three phases exist at a point. How about four phases? Is there a particular pressure and temperature? Is there a possible pressure and temperature at which water, steam, let's say ice 1, let's say ice 9, and this will be a reminder to go read Kurt Vonnegut if you haven't. Normally, it is your freshman or sophomore year of undergrad when someone tells you to go read Kurt Vonnegut. You know, it's like one of those George Orwell books, right? Everyone goes mumbling 1984, and they have probably not read it at some point. When you get older, this will be one of those books that we'll talk about, or Kurt Vonnegut. So you can read it, it's a good book. So why is that possible that there is a pressure temperature area or line or a point at which four phases can coexist? Why or why not? We can't answer that. Turns out it cannot. And Gibbs phase rule allows us to answer that. You cannot have more than four phases coexisting at the same point. So when you become, I don't know, CEO of some company and someone comes up with a phase diagram for a new chemical they have just made, you can directly look at it. And if they have four phases existing at the same point, you can say, this is wrong. This is wrong. You're cheating. You have done something bad. And Gibbs phase rule allows us to say that. So Gibbs phase rule says that F is equal to C minus P plus 2. And this F is the number of degrees of freedom. So what do I mean by number of degrees of freedom? Number of degrees of freedom is the number of intensive variables that can be independently varied. So at a point, how many degrees of freedom do you have? How many intensive variables can you vary at a point? 0, right? It's 1 point. There is no freedom. You're stuck there. Along a line, how many degrees of freedom do you have? 1. You can vary. You might think, well, I can vary my pressure and temperature. But anytime you have a particular temperature along a line, you immediately know what is the pressure it's going to take, right? So along a line, so along a point, number of degrees of freedom is 0. Along a line, number of degrees of freedom is 1. What is the number of degrees of freedom in this area? 2. You can vary pressure and temperature independently. The whole key word here is independent variation, okay? So along this area, degree of freedom is equal to 2 because P and T can be varied independently. So what Gibbs phase rule does is tells you that if you know the number of components you have, and if you know the number of phases you are looking at, you can calculate the number of degrees of freedom. So let's look at it just once, and then next time we will continue from here. Let's do it. Actually, let's do it over here for water. So in this solid area, how many phases do we have? 1, right? We are not talking about other polymorpho We are just talking about one phase. How many components do we have in water? 1. So if you do C minus P plus 2, what do you get for F? 1 minus 1 plus 2 is equal to 2. Therefore, you can vary 2 degrees of freedom independently. So this is Gibbs phase rule. If you put it over here, you will see P is equal to 3, C is equal to 1. Therefore, F is equal to 1 minus 3 plus 2 is equal to 0. You get 0 degrees of freedom. And now you can see if you increase the phases to 4, number of degrees of freedom will become -1. It's simply not possible. So next time, we are going to look at chemical. We are not ready to prove this Gibbs phase rule yet. We have to think about chemical potential a bit more, and then we will come back and prove this later this week.